In the winter of 1916, a man was dying on the Russian front. He had a skin disease that was slowly destroying him from the outside in, and he was lying in a field hospital while the war went on around him. And yet what he was thinking about was not the war, and not his own body failing. He was thinking about a set of equations a man named Einstein had published only months before. Out there in the cold and the noise, Karl Schwarzschild did the arithmetic in his head, and on whatever paper he could find, and he discovered something that frightened even the man whose theory it came from. He found that if you took any amount of matter and crushed it down small enough, gravity would close over it like a hand closing into a fist, and nothing, not light, not information, not even the future, would ever come back out. He sent his work to Einstein by post. Then, a few months later, he died. He never lived to see what he had found, and for a long time almost nobody believed it could be real. That is where this begins, not with a telescope, not with a photograph, with a dying soldier doing mathematics in a trench, finding the edge of a door that the universe had kept closed for 13 billion years. We use the words black hole as if they describe a single thing, as if somewhere out in space there is one kind of object, dark and round and hungry, and that is the whole story. Tonight you're going to learn that this is not even slightly true. There is no such thing as the black hole. There is a family of them, a whole taxonomy, sorted by size and by birth and by behaviour, ranging from objects so vast that light would need weeks to cross their shadow, all the way down to things so small they could hide inside the space between the atoms of your own hand. Some of them we have photographed, some of them we have only heard, ringing through the fabric of space like a struck bell, and some of them, the strangest ones, may be drifting through the room you're in right now, passing through your body, through the wall behind you, through the planet beneath you, and leaving no mark at all. Stay with me as we go through every type, one at a time, from the ones born in the death of ordinary stars to the ones that should not exist at all. There is no rush here. Let your shoulders drop. Let the weight of the day go. We have a long way to travel, all the way out to the edge of what we can see, and all the way back into something smaller than a single grain of dust. And we're going to take it slowly, the way you would walk through a museum after closing, when the lights are low and the halls are empty and you have all the time in the world. Here is the first thing to understand, the idea that makes every type of black hole possible. Gravity is not really a force in the way you were taught as a child. It is not a rope pulling you down. It is the shape of space itself. Mass bends the space around it, the way a heavy stone resting on a stretched sheet makes a dip that smaller objects roll toward. The Earth bends space a little. The Sun bends it more. And if you keep adding mass, or keep crushing the same mass into a smaller and smaller volume, the dip gets steeper and steeper, until at some point it stops being a dip and becomes something else. A well with no bottom. A slope so steep that the speed you would need to climb back out of it exceeds the speed of light. And since nothing in the universe can move faster than light, nothing that falls past that point can ever return. That boundary, that line in empty space past which there is no coming back, has a name. The event horizon. It is not a surface. There is nothing there to touch. It is simply the place where the future stops pointing outward and starts pointing only in. This is the part that unsettles people the first time they truly sit with it. A black hole is not made of anything you could grab. The event horizon is a mathematical edge in empty space. You could cross it without feeling a thing. There would be no wall, no membrane, no warning. One moment you're outside and the entire universe is still available to you. Every star, every direction, every possible tomorrow. The next moment you're inside and there is exactly one direction left, and it leads in, and the word for that direction is no longer down or forward. The word for it is later. Inside a black hole, the center is not a place. It is a time. It is your future, and you cannot avoid it any more than you can avoid the arrival of next Tuesday. Schwarzschild found the size of that boundary for any given mass, and the formula is almost insultingly simple. Tell me how much mass you have, and I can tell you exactly how small you would need to crush it to make a black hole. For the Sun, the answer is a sphere about 3 kilometers across. For the entire Earth, with all its oceans and mountains and the molten iron at its heart, the answer is a sphere the size of a marble, less than a centimeter, everything you have ever stood on, everything you have ever known, compressed to something you could hold between 2 fingers and never see again. That is how reluctant the universe is to make these things, and also how absolute it is once it does. The recipe is everywhere. The conditions almost never are. And for decades, that was the problem. The mathematics said these objects could exist. Einstein himself did not like it. He spent years trying to argue that nature would find some way to prevent it, some last barrier that would stop matter from collapsing all the way down. He was wrong, and he was not the only great mind to be wrong about this. The idea sat in the equations like a splinter, undeniable on paper and impossible to believe. It took the better part of a century, and the deaths of stars far larger than our own, and instruments more sensitive than anything previously built by human hands, to drag the black hole out of the mathematics and into the catalogue of real things. And when it finally arrived, it did not arrive as one object. It arrived as many. So here is the map of where we are going, the shape of the journey, so you know the road, even as you start to drift. We will begin with the most common kind, the workhorse of the cosmos, the black hole that forms when an ordinary massive star runs out of fuel and falls in on itself. There are hundreds of millions of them in our galaxy alone, and the nearest one is closer than you would like. Then we will go to the first one humanity ever detected, not by light, but by sound, by the way it shook the universe when it collided with another. From there we will hunt for the missing middle, a class of black hole so elusive that for years some scientists doubted it existed at all. We will travel to the centre of our own galaxy and stand at the edge of the monster that lives there, 4 million times the mass of the Sun, around which everything you have ever called home is slowly turning. We will look at the first black hole ever photographed and learn what that famous orange ring actually is. We will go further out still to the ultramassive giants, objects so large they strain the limits of what we thought was possible. We will go back in time to the early universe, to black holes that are too big and too old and that no one can yet fully explain. And finally we'll come back down, all the way down, smaller and smaller, to the black holes that may have been born in the first second after the beginning of everything, the ones that could be invisible, the ones that could be passing through you as you breathe. That last category is why I told you to stay until the end, because the journey out to the largest things in the universe is beautiful, and it is humbling, and it will make you feel very small in the good way, the way a clear night sky makes you feel small. But the journey back in, to the smallest and the strangest, is where the real unease lives. Not fear exactly, something quieter than fear. The sense that the thing you assumed was rare and far away might really be common and near, and that the universe has simply chosen not to tell you. For now, let go of all of that. Settle into the idea that you're about to take a slow walk through a family of objects that bends time, that erases information, that turns stars into silence and silence into the loudest thing in the cosmos. You do not need to remember any of it. You do not need to understand the mathematics. You only need to follow the sound of it, the way the names get larger and then smaller again, the way the distances stretch out and fold back. Breathe in slowly, hold it for a moment at the top, and let it out, longer than you took it in. The first member of the family is the one that started it all. Not the largest, not the strangest. The most ordinary, in the way that the most ordinary things are often the most quietly astonishing once you look at them closely. It is the black hole that begins its life as a star not so different from the one that warms your sky, only larger, and it is born in one of the most violent events the universe is capable of producing. To understand it, we have to watch a star die. Part 2, the ones born from the death of stars. Picture a star far larger than our Sun, not twice as large, not 3 times, but 20 or 30 or 40 times its mass. A colossal furnace of hydrogen burning so hot and so fast that it lives only a few million years instead of the leisurely 10 billion our own star will enjoy. For all of that short blazing life, the star is locked in a single argument with itself, an argument it can never truly win. Gravity wants to crush it inward. The heat and pressure of the fusion in its core wants to push it outward. As long as there is fuel to burn, the outward push holds the line, and the star stays the size it is, a balance so steady that from the outside it looks eternal. But it is not eternal. It is a clock counting down, and the fuel is finite, and gravity is patient in a way that nothing else in the universe is patient. The star burns hydrogen into helium. When the hydrogen in the core runs low, it begins burning helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon, each stage faster than the last, each one a more desperate attempt to keep the fire going against the inward pull. By the end, the star is burning silicon into iron, and that is where the argument finally turns. Iron is the ash that cannot burn. Fusing iron does not release energy, it absorbs it. So in the heart of this dying giant, in a matter of moments, the fire goes out. The outward push vanishes, and gravity, which has been waiting for millions of years, takes the whole thing in less than a second. The core collapses. An object larger than the Earth falls inward to the size of a city in the time it takes you to blink. The infalling outer layers crash down onto the collapsing core, rebound, and tear the star apart in an explosion so bright that for a few weeks it can outshine the entire galaxy that contains it. That is a supernova. You've probably seen the images, those expanding shells of glowing gas, beautiful and ragged, the wreckage of something enormous. But the supernova is only the visible part, the part that gets the attention. The real story is what happens at the very centre, in the collapsing core that the explosion leaves behind. If the leftover core is somewhat heavy, around 1.5 times the mass of the Sun, it becomes a neutron star, an object so dense that a single teaspoon of it would weigh as much as a mountain. The collapse halts there, held up by a strange quantum stubbornness, the refusal of neutrons to be packed any tighter. But if the core is heavier still, past a threshold that physicists call the Tolman-Oppenheimer-Volkoff limit, somewhere around 2 to 3 solar masses, then even that quantum stubbornness fails. There is nothing left in the known laws of physics that can stop the fall. The core keeps collapsing, smaller and smaller, denser and denser, past the neutron star, past anything we have a name for, until it disappears behind its own event horizon and becomes a stellar mass black hole. That is the most common kind of black hole in the universe. It is the workhorse. It is the one the cosmos makes again and again, every time a sufficiently massive star reaches the end of its life, and massive stars are dying somewhere in the observable universe constantly, all the time, far faster than you could count. A typical stellar mass black hole holds something like 5 to a few dozen times the mass of our Sun, all of it compressed into a region perhaps a few tens of kilometres across. You could fit one inside a small city, and it would weigh more than the entire solar system minus the Sun, and it would be utterly perfectly dark. Now here is the number that should make you sit up a little, even as you are trying to fall asleep. In our galaxy alone, in the Milky Way, astronomers estimate there are hundreds of millions of these stellar mass black holes. Some estimates run as high as 100 million, others push past that. Hundreds of millions of small, dark, dense objects scattered through the galaxy, most of them invisible, most of them undetected, most of them simply drifting through the dark between the stars where they were born, having long ago finished the explosions that made them. They do not glow. They do not announce themselves. A black hole sitting alone in space with nothing falling into it gives off no light at all. It is the perfect hiding thing, and there may be 100 million of them in our galaxy, and we have directly confirmed only a tiny, tiny handful. So the obvious question, the one that arrives in the quiet of a night like this, is how close is the nearest one? And the honest answer is that we are not entirely sure, because we cannot see most of them, and that uncertainty is itself a kind of answer. For a long time, the closest confirmed stellar mass black hole was thought to be over 1,000 light-years away. Then, in 2022, astronomers found one much closer, using a method that does not require the black hole to glow at all. They watched a perfectly ordinary star, a star a lot like our Sun, and they noticed it was wobbling. It was orbiting something. Something with the mass of about 10 suns. Something that gave off no light. They named the object Gaia BH1 after the spacecraft that helped find it, and it sits roughly 1,500 light-years from Earth in the direction of the constellation Ophiuchus. In cosmic terms, that is practically next door. It is closer to us than many of the stars you can see with your naked eye on a clear night. And Gaia BH1 is almost certainly not the closest. It is just the closest one we have managed to catch in the act of betraying itself, by tugging on a visible companion. The truly isolated ones, the ones drifting alone with nothing nearby to disturb, are essentially silent. There could be one a few hundred light-years away. There could be, in principle, one far closer than that, and we would have no easy way to know, because a stellar mass black hole passing through the empty dark, with no gas to swallow and no star to orbit, is one of the most genuinely invisible objects the universe contains. And yet there is one way, a beautiful and difficult way, to catch even a perfectly isolated black hole drifting alone through space. Einstein's theory tells us that a massive object bends the path of light passing near it, acting like a lens. So if a lone black hole happens to drift directly in front of a distant background star, its gravity will briefly bend and magnify that star's light, causing the star to appear to brighten and then fade over the course of weeks or months as the black hole passes by. There is no glow from the black hole itself, only this fleeting distortion of a star far behind it, a momentary flaring caused by an invisible mass crossing the line of sight. Astronomers spent years watching for exactly this, sifting through the brightening and dimming of millions of stars, and after a long and careful effort they confirmed what is regarded as the first solitary, wandering black hole ever found. A stellar mass black hole drifting alone through the galaxy with no companion at all, betrayed only by the way it bent the light of a star thousands of light years beyond it. It was the first direct proof that the galaxy truly is populated by these lonely drifters, the invisible ones, the ones with nothing nearby to give them away, exactly as the hundreds of millions had long implied. This is not a reason to be afraid. The distances are still vast beyond comprehension, and the chance of one ever coming near our solar system is so small as to be meaningless across the entire lifespan of the Sun. But it is a reason to feel the strangeness of it. The galaxy you live in is salted with these things. The dark between the stars is not empty. It is populated. There is a way to picture how a stellar mass black hole behaves when it does have something nearby, and it is one of the more haunting images in all of astronomy. Imagine two stars born together, a pair, orbiting each other as many stars do. One of them is much more massive than the other, so it lives fast and dies first, collapsing into a black hole. Now the black hole and its surviving companion star continue to orbit, locked together, and if they are close enough, the black hole begins to pull material off the outer layers of the living star. That stolen gas does not fall straight in. It spirals, the way water spirals toward a drain, forming a flat, swirling disk that wraps around the black hole and grows hotter and hotter as it is squeezed and accelerated. By the time the gas reaches the inner edge of that disk, it is moving at a significant fraction of the speed of light and has been heated to millions of degrees, hot enough to scream in X-rays across the galaxy. That is how we found the very first stellar mass black hole ever identified, an object called Cygnus X1. Detected in the 1970s as a powerful X-ray source with an invisible heart. A star slowly being eaten, its stolen substance lighting up the boundary of the thing devouring it. The black hole itself stays dark. It is the dying gas around it that gives it away. Sit with that pairing for a moment, because it is the essential shape of how we find most of these objects. The black hole reveals itself only through what it does to others. It is detected by the wobble of a star it pulls on, by the glow of gas it strips away, by the gravitational shadow it casts on everything in its reach. It never speaks for itself. It is known entirely by its effect on its surroundings, the way you might know a person had passed through a room, only by the things they moved and the people they changed. There is something almost philosophical in that, and on a night like this you can let the thought drift wherever it wants to go. The most absolute objects in the universe, the ones from which nothing escapes, are knowable only through their relationships. The darkest things are visible only in the light of what is near them. But for all their power, all their hunger, all the violence of their birth, there is a ceiling on how large a stellar mass black hole can be. A star can only be so massive before it tears itself apart in other ways, and the black hole it leaves behind can only be so heavy as a result. The very largest stellar mass black holes top out at a few dozen times the mass of the Sun, perhaps a little more in special cases. They are common, they are everywhere, but they are, in the grand scale of the family, small. And that raises a question that troubled astronomers for a long time, a question that takes us to the next member of the family. If stellar collapse can only make black holes of a few dozen solar masses, and if the centres of galaxies hold black holes of millions or billions of solar masses, then how do you get from one to the other? What fills the enormous gap in between? The answer, it turned out, was not easy to find, and the search for it became one of the great hunts in modern astronomy. But before we go searching for that missing middle, we have to talk about the moment everything changed. The moment we stopped only seeing black holes and started, for the first time in human history, to hear them. Part 3, the first one we ever heard. For most of human history, astronomy was the science of light. Everything we knew about the sky, we knew because light from distant objects had travelled across space and entered our eyes, or our telescopes. The stars, the planets, the galaxies, all of it arrived as light, in one form or another, visible or infrared or radio or X-ray, but always light, always some part of the electromagnetic spectrum. And that meant black holes posed a unique kind of problem, because a black hole gives off no light. We could see the gas around them, we could see the stars they pulled on. But the object itself, the thing behind the event horizon, was permanently beyond the reach of every telescope ever built, not because they were too far away or too faint, but because they emit nothing to be seen. For a black hole sitting alone, undisturbed, light is simply the wrong sense. You cannot look at silence. But Einstein, the same man whose equations Schwarzschild had solved in that field hospital, had predicted something else, almost as an afterthought, a consequence of his theory that he himself doubted would ever be measurable. He predicted that when massive objects accelerate, they should send out ripples in the fabric of space itself, not light, not anything travelling through space, but a disturbance of space, a stretching and squeezing of distance that radiates outward at the speed of light, like the ripples from a stone dropped in a pond. He called them gravitational waves, and he was almost certain we would never detect them, because the effect was so unimaginably tiny. By the time one of these ripples reached the Earth from somewhere out in the cosmos, it would stretch and shrink the distances around you by an amount smaller than the width of a single proton, across the entire length of a 4-kilometre instrument. To measure that is like measuring the distance to the nearest star and detecting a change the width of a human hair. It seemed hopeless. For 100 years it seemed hopeless. And then, on the 14th of September, 2015, at a few minutes before 5 a.m. Central European Time, the impossible happened. 2 enormous detectors, one in Louisiana and one in Washington State, each a pair of perpendicular tunnels 4 kilometers long, with laser beams bouncing back and forth inside them, both registered the same fleeting shudder, milliseconds apart. A signal that rose in pitch and intensity over a fraction of a second and then abruptly stopped. Scientists call it a chirp because if you translate the wave into sound, that is exactly what it is. A rising tone, a swoop upward, and then silence. The first thing humanity ever heard from a black hole was a single rising note, lasting 1/5 of a second, that had been travelling toward us for more than 1 billion years. Here is what made that note. More than 1 billion years ago, in a galaxy whose name we will never know, 2 black holes were locked in a death spiral. Both were stellar mass black holes, the kind we just talked about, the kind born from dying stars. One was about 36 times the mass of the Sun, the other about 29. They had been orbiting each other for an unknowable length of time, and as they orbited they radiated away their energy as gravitational waves, which caused them to spiral closer and closer together, faster and faster. In the final moments they were whipping around each other dozens of times per second. 2 objects each heavier than 30 suns, circling at a significant fraction of the speed of light, warping space so violently that the ripples carried more power than all the light from all the stars in the entire observable universe combined. And then they touched. They merged into a single, larger black hole. And in the instant of that merger, something happened that is hard to even hold in the mind. The 2 black holes had a combined mass of about 65 suns. The black hole they formed had a mass of about 62. 3 solar masses had vanished. 3 times the entire mass of our Sun had been converted in a fraction of a second into pure gravitational energy, into the ripples in space that would eventually wash over the Earth and move those laser beams by less than the width of a proton. 3 suns, gone, turned into a wave. That is the most powerful single event ever detected by human instruments, and it happened in total silence, in total darkness, emitting no light whatsoever, announced to us only by the trembling of space itself 1 billion years later. Think about the timing of it for a moment, because it is the kind of thought that does something to your sense of scale. When those 2 black holes finished their long collision and sent that wave outward, there was no complex life on Earth. The most advanced organisms on our planet were single cells. The wave travelled outward at the speed of light across the empty dark for hundreds of millions of years. While it travelled, The first animals appeared in Earth's oceans. While it travelled, life crawled onto land. While it travelled, the dinosaurs rose and ruled and were wiped away. Mammals spread. The first humans stood upright, learned to make fire, painted on cave walls, built cities, fought wars, wrote symphonies, split the atom, and finally, just barely, just in time, built two instruments precise enough to feel the wave when it arrived. It reached the Earth in the same century that we finished the machines capable of noticing it. A few decades earlier, and it would have passed straight through the planet, through every living thing, unnoticed and unrecorded, as countless such waves surely had before. We caught the very first one essentially the moment we became able to. That is either an extraordinary coincidence or a quiet reminder of how recently we arrived at this particular window, blinking, looking out at a universe that had been speaking this language the whole time. The detection of that wave, the event scientists named GW150914 after the date it arrived, did something that decades of theory could not. It proved, beyond any reasonable doubt, that black holes are real, physical objects that exist and move and collide in the universe. Until that moment, every piece of evidence had been indirect. The wobbling stars, the glowing gas, the X-ray sources, all of it was consistent with black holes, but could in principle be explained other ways if you were stubborn enough. The gravitational wave was different. The shape of that chirp, the exact way it rose and stopped, matched the predictions for two black holes merging so precisely that there was simply no other explanation. We had not just inferred a black hole, we had recorded the sound of two of them becoming one. The scientists who built those detectors received the Nobel Prize, and they deserved it, because they had opened an entirely new sense for humanity. For the first time, we could hear the universe as well as see it. And the very first thing we heard was the death song of two black holes. Since that morning in 2015, the detectors have gotten better, and the catalogue has grown. We have now heard dozens upon dozens of these mergers, black holes colliding with black holes, neutron stars colliding with neutron stars, black holes swallowing neutron stars whole. Each one arrives as a chirp, a rising note from somewhere out in the dark, the final cry of objects that finished their collision millions or billions of years ago. There is a strange and beautiful melancholy to it, if you let yourself feel it. We are listening to a sky full of events that are already long over. Every chirp is a recording, played back across an enormous gulf of time, of a moment that ended before our species existed. We are an audience arriving very late to a performance that has been going on since the beginning, finally able to hear the music, knowing that all the musicians have long since fallen silent. There is also a deeper sound, discovered only recently, that is not a single chirp at all, but a continuous low hum filling the entire universe. The detectors in Louisiana and Washington can only hear the brief, high collisions of stellar mass black holes. But the largest black holes of all, the giants at the centres of galaxies, which we will come to soon, also collide when their galaxies merge, and those mergers produce gravitational waves of enormous slow wavelength, ripples that take years to rise and fall rather than fractions of a second. No instrument on Earth is large enough to detect waves that slow, so astronomers use something far larger. They use the galaxy itself. Scattered across the sky are dead stars called pulsars, spinning rapidly and flashing beams of radio energy past the Earth with the regularity of cosmic clocks, ticking with astonishing precision. And in 2023, after watching dozens of these pulses for many years, astronomers announced that the ticking was very slightly, very subtly off, all across the sky, in a coordinated pattern that could only be explained by gravitational waves washing through the entire galaxy, stretching and squeezing the distances between us and the pulsars by tiny amounts. They had detected a background hum, a low continuous drone of gravitational waves, the combined murmur of countless pairs of supermassive black holes circling each other across the whole observable universe. The cosmos, it turns out, is not silent in this language. It is filled with a faint, constant sound, the slow song of giants spiralling toward one another in galaxies beyond counting, and we have only just learned how to hear it. And among those dozens of mergers, hidden in the growing catalogue, were a few signals that did not quite fit the expected pattern. A few chirps that, when astronomers worked backward from the shape of the wave to the mass of the objects that made it, pointed to black holes that were too heavy. Not stellar mass, not the few dozen suns that dying stars can produce. Heavier, much heavier in some cases than the theory said collapsing stars should be able to make. These were the first real fingerprints of a class of object that had been suspected for decades but never confirmed. The missing piece of the puzzle, the gap in the family that nobody could fill. To hear them was one thing. To understand what they were and why they had been so impossible to find is the next part of the story. We're going looking for the awkward middle child of the black hole family, the one that, until very recently, some serious scientists were not sure existed at all. Part 4. The Missing Middle. To understand why the next type of black hole was so hard to find, you have to understand the strange shape of the family as astronomers first mapped it. At one end, there were the stellar mass black holes, the ones we have been discussing, ranging from a few times the mass of the Sun up to a few dozen. Common, everywhere, born from the deaths of stars. At the other end, far across the catalogue, there were the giants, the black holes at the centres of galaxies, holding millions or even billions of times the mass of the Sun. We will get to those, they are extraordinary. But between those two populations, between a few dozen solar masses and a few million, there was a vast gaping emptiness, an entire range of sizes spanning thousands of times in mass, where almost nothing seemed to live. It was as if you went looking for animals and found insects and found elephants, but could not, no matter how hard you searched, find anything in between. No cats, no dogs, no horses, no, just the very small and the very large, and a silence where the middle should be. This middle category got the unglamorous name of intermediate mass black holes, and for years they were the awkward child of the family. Astronomers expected them to exist. There seemed to be no reason they should not. You can imagine plenty of ways to make one. Take a handful of stellar mass black holes in a dense cluster of stars and let them collide and merge, again and again, building up something larger. Or imagine the very first stars in the universe, which theories suggest were far more massive than anything that forms today, hundreds of times the mass of the Sun, collapsing directly into black holes of 100 or 1,000 solar masses. Or imagine clumps of gas in the early cosmos collapsing all at once, skipping the star stage entirely. There were many plausible recipes, and yet for the longest time, almost none of the expected objects turned up. The middle of the family was a desert, and nobody was entirely sure why. The trouble is that an intermediate mass black hole is, in a sense, the hardest size of black hole to catch. The small ones, the stellar mass ones, often live in pairs with visible stars, and that gives them away through the wobble and the stolen gas and the X-rays. The enormous ones, the galactic giants, are surrounded by whole swirling cities of stars and gas, lighting up brilliantly as material falls in, blazing as quasars visible across the entire universe. But the intermediate ones tend to live in lonely places, in the cores of old, quiet star clusters, with relatively little gas to fall in and light them up, and relatively few close companions to tug on in obvious ways. They are large enough to be rare and small enough to be dim. They fall into a detection gap, a blind spot built into the methods we had. For decades, the search for them turned up only candidates, only maybes, only objects that might be intermediate mass black holes if you interpreted the ambiguous data one way, and might be something else entirely if you interpreted it another. Every few years there would be an announcement, a promising signal in a globular cluster, or a faint source in a small galaxy. And then the debate would begin, and the case would weaken, and the desert would remain. One of the better candidates carried the kind of name that only an astronomer could love, a string of numbers and letters describing its position in the sky. It sat at the edge of a distant galaxy, a powerful X-ray source that flared and faded, far too bright to be a stellar mass black hole feeding normally, and yet not in the centre of a galaxy where the true giants live. Estimates put it somewhere in the thousands of solar masses, right in the heart of the missing range. For a while it was the strongest piece of evidence we had, but even that, like all the others, came wrapped in uncertainty, dependent on assumptions, arguable. The pattern held. The middle of the family refused to step fully into the light. And then the new sense arrived. The gravitational wave detectors, the same instruments that had heard those first stellar mass black holes colliding, kept listening, and the catalogue kept growing, and buried within it came the signals that finally broke the silence. In May of 2019, the detectors recorded a chirp from two black holes merging, and when the scientists worked backward to find the masses, the numbers were startling. The two original black holes were each far heavier than ordinary stellar collapse should easily produce, and the object they formed when they merged came in at around 140 times the mass of the Sun. That was over the line. That was, by the standard definitions, the first reasonably direct detection of an intermediate mass black hole forming, witnessed in the act of its birth, assembled from the collision of two smaller monsters. The desert had a resident at last, caught not by light, but by the trembling of space. It did not stop there. The detectors grew more sensitive, and the listening continued, and in November of 2023 they recorded something even more extreme. A signal that the collaboration spent more than a year analysing before announcing it to the world in 2025. It came from the merger of two of the most massive black holes ever heard, each one well over 100 times the mass of the Sun, colliding to form a single object of roughly 225 solar masses. That is deep into intermediate territory, and what makes it especially fascinating is that the two black holes that merged were themselves in a mass range that ordinary stellar collapse is thought to forbid, a range physicists call the mass gap, where the explosions of dying stars are supposed to leave nothing behind at all. So how did they get there? The leading idea is that they were not made by single stars at all, but were themselves the products of earlier mergers, black holes built from black holes, each generation assembling from the wreckage of the one before, a kind of cosmic accumulation happening in the crowded hearts of dense star clusters. If that is right, then we are not just seeing intermediate mass black holes. We are seeing, in real time, the process by which the universe might build its way from the small to the large, one collision at a time, climbing the staircase of mass that connects the workhorses to the giants. That possibility matters more than it might first appear, because it touches one of the deepest open questions in all of astronomy. The giants at the centres of galaxies, the supermassive black holes, are so enormous that nobody's entirely sure how they came to be, especially the ones we see in the very early universe, which seem to have grown impossibly large, impossibly fast. One leading idea is that they started as intermediate mass seeds, that the seed of every galactic giant was once a black hole of a few hundred or a few thousand solar masses, which then grew over billions of years by swallowing gas and merging with others until it became the monster we see today. If that is true, then the intermediate mass black hole is not just a missing middle, it is the missing origin. It is the childhood photograph of the largest objects in the universe, the stage every giant must have passed through on its way to becoming what it is. Find enough of them, understand how they form, and you begin to understand where the giants come from, which is one of the questions astronomy most desperately wants to answer. And yet, even now, even after the gravitational wave detections, the intermediate mass black hole remains the most uncertain and contested member of the family. We have heard a handful being born in collisions. We have a scattering of candidates glowing faintly in distant clusters, but we have not yet built up a clear, confident population of them, the way we have for the small and the large. They remain elusive, half-glimpsed, more inferred than seen. Some questions about them are genuinely open, and good scientists still argue about the details, about exactly how many there are, about exactly how they form, about whether some of the candidates are real. That uncertainty is not a weakness in the story. It is the story. It is what it actually looks like to stand at the frontier of knowledge, where the desert is only just beginning to show its first signs of life, where the data is real, but the interpretation is still being argued out in conference halls and journal pages. You are listening right now to a chapter of astronomy that is still being written, a search that is still underway, a part of the family that the universe has only barely begun to reveal. So we have the small ones, born from dying stars, and we have the elusive middle, glimpsed in collisions and faint flares. But we have not yet faced the giants. We have not yet gone to the place where the true monsters live, the places around which entire galaxies are organised, the gravitational anchors at the hearts of the larger structures in the cosmos. And to find the nearest one of those, we do not have to look across the universe at all. We only have to look toward the centre of our own galaxy, toward the constellation Sagittarius, toward a point in the sky that is at this moment very likely below your horizon, on the other side of the Earth, hidden by the planet itself. Because the nearest supermassive black hole, the giant at the centre of the Milky Way, is something we are not approaching from the outside. It is something we are already inside the gravitational embrace of. It is, in the truest sense, the thing we're all orbiting. Part 5. the monster at the centre of everything. There is a direction you could point right now, from wherever you're lying, that aims straight at the centre of the galaxy. It runs through the floor or through a wall, through the rock and iron of the Earth, out the other side and across 26,000 light-years of stars and dust and dark. And at the end of that line, at the very heart of the Milky Way, there is a black hole. It has a name that sounds almost gentle, Sagittarius A star, written as SGRA, with a little asterisk after it. The asterisk a quiet convention that astronomers use to mark the compact radio source at a galaxy's core. That gentle name belongs to an object with the mass of about 4 million suns compressed into a region smaller than the orbit of Mercury, and everything you have ever known, every star you have ever seen, the sun, the Earth, you, all of it is slowly, endlessly circling that point. Let that settle for a moment. The sun is not still. It is moving, carrying the entire solar system with it, in an enormous orbit around the centre of the galaxy, around Sagittarius A star. We are travelling at something like 230 kilometres every second, an almost incomprehensible speed, and even at that speed it takes the sun roughly 225 million years to complete a single lap. The last time the sun was in the position it occupies now, relative to the galactic centre, the dinosaurs had not yet evolved. The continents wore different shapes. An entire galactic year, one full orbit around the central black hole, is longer than the age of most of the species that have ever lived on Earth. You are, at this moment, partway through one such lap, a passenger on a journey that began long before you were born, and will continue long after, around a dark anchor you will never see, that holds the whole spinning city of the galaxy together. For a long time, the idea that there was a black hole at the centre of our galaxy was a suspicion rather than a certainty. The centre of the Milky Way is hidden from us. When we look towards Sagittarius, we are looking through the thickest, dustiest part of the galaxy, through layers of gas and stars that block visible light almost completely. You cannot simply point an ordinary telescope at the galactic centre and see what is there. The dust swallows the view. But other kinds of light pass through that dust more easily. Infrared light and radio waves, and when astronomers began studying the centre in those wavelengths, they found something deeply strange. They found a compact, intense source of radio energy, sitting almost exactly at the gravitational centre of the entire galaxy, not moving, not drifting, anchored in place while everything around it turned. And then they began to watch the stars near that point, and the stars near that point were doing something that only one kind of object could explain. This is one of the great achievements of modern astronomy, and it is worth slowing down for, because of how patient it was. Starting in the early 1990s, two teams of astronomers, one led by Reinhard Genzel and one led by Andrea Ghez, began tracking individual stars in the crowded region around Sagittarius A star, watching them year after year after year, building up images of their motion across decades, and what they saw was extraordinary. The stars were not drifting lazily, they were racing on tight elongated orbits around an invisible point. One star in particular, a star given the name S2, swings around the central object on an orbit that takes only about 16 years to complete, and at its closest approach it whips past the dark centre at more than 5,000 kilometres every second, more than 2% of the speed of light. Imagine that. A star, an entire sun hurled around an empty-looking point at thousands of kilometres per second, year after year, decade after decade, tracing out a clean elliptical orbit around something that gives off no light of its own. The only thing that can hold a star on such an orbit, the only thing with enough mass packed into a small enough space, is a supermassive black hole. By watching S2 and its companions complete their laps, the two teams could weigh the invisible centre with great precision, 4 million suns, in a space smaller than our planetary neighbourhood. There's nothing else in physics that can be that heavy and that small and still emit so little light. It had to be a black hole. The work was so definitive, so careful, so decades-long in its patience, that Genzel and Ghez were awarded the Nobel Prize for it in 2020. What makes Sagittarius a star different from the stellar mass black holes we began with is not just its size. Though 4 million suns is an enormous step up from a few dozen, it is its role. A stellar mass black hole is a leftover, a remnant, the ash of a single dead star, drifting through the galaxy as one object among hundreds of millions. A supermassive black hole is something else entirely. It sits at the gravitational center of an entire galaxy, hundreds of billions of stars arranged around it, and the galaxy and the black hole appear to be bound together in ways we are still working to understand. There is a strikingly tight relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself, a correlation so precise that it cannot be a coincidence. It is as if the black hole and the galaxy grew up together, shaping each other, the black hole's appetite somehow regulating the galaxy's growth, the galaxy's structure somehow feeding the black hole. The giant at the center is not a passenger. It is, in some sense we do not fully grasp, a partner in the existence of the whole, and our own galaxy's giant is, by the standards of supermassive black holes, rather quiet. Sagittarius, a star, is not actively gorging itself right now. There is relatively little gas falling into it at the moment, which means it does not blaze brilliantly the way some galactic centers do. It is a sleeping giant, dim and calm, occasionally flickering as a small clump of gas wanders too close and is briefly heated before it falls in or is flung away. But it has not always been so quiet, and it may not stay quiet forever. There is evidence written in the gas above and below the plane of the galaxy of enormous bubbles of energy that seem to have been blown out from the center in the relatively recent past, perhaps a few million years ago, as if the black hole woke briefly and fed and roared, and then went back to sleep. We live near a giant that mostly slumbers, that we cannot see, that holds us in our long, slow orbit, that has eaten before and may eat again, and that will, in all likelihood, still be sitting at the center of this galaxy, long after the sun has died, and the Earth is gone, and there is no one left to point a telescope towards Sagittarius and wonder what is hidden in the dust. There is a temptation, when you first absorb all of this, to feel afraid, as if living in a galaxy with a 4 million solar mass black hole at its center were a kind of danger. It is not. The galactic center is 26,000 light-years away, an almost meaningless distance to anything that might fall in. The sun will never go anywhere near it. Our long orbit is stable, has been stable for billions of years, and will remain stable for billions more. The black hole at the center of the Milky Way is not a threat lurking in the dark. It is more like a cornerstone, the still point around which the entire structure of our home is built, the anchor that keeps the whole vast pinwheel of stars from flying apart. When you feel the planet beneath you tonight, you are not only resting on the Earth, you are riding on a world that is riding around a star that is riding around a black hole, all of it turning together, slowly, gracefully, on a journey that has no destination except the next lap and the next and the next. For a long time, that was as close as we could get. We could weigh it. We could watch the stars dance around it. We could infer everything about it from its effects. But we could not see it, not the object itself, not the shadow it casts, not the boundary of the thing. The dust was too thick, the object too small on the sky, the technology not yet equal to the task. To actually photograph a black hole, to capture an image of that dark boundary against the glow of the matter around it, seemed for decades like a fantasy, the kind of thing that would forever live only in artists' impressions and computer simulations. And then, in the span of a few years, an extraordinary collaboration of scientists turned the entire Earth into a single telescope and did the thing that could not be done. They took the picture. And the first black hole they photographed was not the one at the center of our own galaxy. It was a far larger and far more distant giant, the monster at the heart of another galaxy entirely, and the image they produced became one of the most famous photographs ever taken, Part 6, the first photograph. The problem with photographing a black hole is not that it is dark. The problem is that it is small. Not small in mass, of course. The giants hold millions or billions of suns, but small in the sky, small in the angle they take up when seen from across the cosmos. A black hole's event horizon, even for one of the largest in the universe, is a tiny thing compared to the distances involved. Trying to photograph one is like trying to read the date on a coin lying on the surface of the moon, from your backyard, with the naked eye. The detail you would need to capture is finer than any single telescope on Earth could ever resolve, finer by far. By every ordinary measure, it was impossible, and so a group of scientists decided to do something that sounds, when you first hear it, almost absurd. If no single telescope was large enough, they would build a telescope the size of the entire planet. This is the Event Horizon Telescope, and the idea behind it is one of the most elegant in modern science. When you link together radio telescopes scattered across the world, observing the same object at the same instant, and you combine their signals with exquisite precision, the array behaves in terms of its ability to resolve fine detail, as if it were a single dish as wide as the distance between the telescopes. So they recruited observatories on mountaintops and high deserts across the globe, from Hawaii to Chile to Spain to the South Pole, and they synchronized them with atomic clocks so accurate they would not lose a second in 100 million years. And on a few clear nights in April of 2017, they all pointed at the same target at the same time and listened. The amount of data they collected was so enormous that it could not be sent over the internet. It had to be recorded onto stacks of hard drives and physically flown, by airplane, to central locations where it could be combined. The data from the telescope at the South Pole could not even be retrieved until the Antarctic winter ended, and flights could resume many months later. 500 tons of hard drives, carrying the faint whispers of a black hole, riding in the cargo holds of ordinary planes. The target they chose for their first great effort was not the black hole at the centre of our own galaxy, even though it is the closest. They chose a far more distant giant, the supermassive black hole at the heart of a galaxy called Messier 87, or M87, an enormous elliptical galaxy, some 55 million light-years away. They chose it because, despite being so much farther than our own galactic centre, it is so vastly larger that it actually appears about the same size in the sky, and because it is more cooperative to observe, a steadier and more reliable target. The black hole at the centre of M87 is a true monster, holding around 6.5 billion times the mass of the Sun, more than 1,000 times heavier than the giant at the centre of the Milky Way. Its event horizon is so large that our entire solar system, the Sun and all the planets, and the vast orbits out to the edge of the planetary realm would fit inside it with room to spare. A beam of light, the fastest thing in the universe, would take days to cross the shadow it casts. This was the object the planet-sized telescope set out to photograph. It took 2 years to process the data, 2 years of careful, painstaking analysis by teams working independently, so they could not unconsciously influence each other toward the answer they expected. And then, in April of 2019, they revealed the image to the world. You have almost certainly seen it. A ring of orange light slightly brighter along the bottom surrounding a dark round centre. It does not look like much at first. It is fuzzy, low resolution by the standards of ordinary photographs, an orange smudge with a hole in the middle. But what you're looking at, when you look at that image, is one of the most profound photographs ever taken by human beings. That dark centre is the shadow of a black hole. It is the region from which no light can escape, silhouetted against the glowing material swirling around it. For the first time in history, humanity was looking directly at the edge of one of these objects, seeing with our own instruments the boundary that Schwarzschild had calculated from a field hospital more than a century before. The door in the equations had finally been photographed. But here is the part that most people miss, the detail that transforms the image from a curiosity into something genuinely strange. That orange ring is not simply a picture of glowing gas in a circle. The ring is larger than you might expect, and the reason is that the black hole's gravity is so powerful that it bends the path of light around itself. Light that should be travelling away from us, light emitted by gas on the far side of the black hole behind it, where you would think it should be hidden, is bent by gravity and wrapped around the event horizon and redirected toward us, so that we see it as part of the ring. We are, in a real sense, seeing around the back of the black hole. The ring is a portrait of light being forced to curve, of the far side of the object brought into view by the warping of space itself. And the reason one part of the ring is brighter than the rest is that the material there is rushing toward us at a large fraction of the speed of light as it orbits, which makes its light appear brighter, while the material moving away appears dimmer. The asymmetry in that smudge of orange is a record of matter circling the drain at speeds we can barely imagine, some of it sweeping toward us, some away, all of it glowing on the last stable ledge before the fall. 3 years later, in May of 2022, the same collaboration finally released their image of the giant at the centre of our own galaxy, Sagittarius A star, and it looked remarkably similar. Another orange ring around a dark heart, a confirmation that these objects share the same essential structure whether they hold 6 billion suns or 4 million. But the image of Sagittarius A star had been far harder to make, and the reason reveals something lovely about the difference between the two. M87's black hole is so enormous that gas takes days to orbit it, which means it changes slowly, holding still long enough to be photographed cleanly, like a mountain that does not move while you set up your shot. Sagittarius, a star, is so much smaller that gas whips all the way around it in mere minutes. The whole scene was flickering and shifting even as the telescopes watched, like trying to photograph a child who will not stop fidgeting, the image blurring with the motion of the very thing they were trying to capture. It took clever new techniques and far longer to tease a clear picture out of that churning, restless, fast-moving light. But they did it. They photographed the dark heart of our own galaxy, the anchor we are all orbiting, the thing hidden behind 26,000 light-years of dust, and they showed it to be exactly what the patient decades of watching dancing stars had told us it must be. The galaxy M87 holds one more secret worth pausing on, because it shows what these giants can do when they feed. Long before anyone photographed its black hole, astronomers had noticed something strange streaming out of the centre of M87, a thin, straight beam of light reaching outward from the core, a structure first spotted more than a century ago in 1918, when no one yet knew what could possibly produce it. We now understand it to be one of the most violent phenomena in the cosmos. As matter spirals into a spinning supermassive black hole, some of it, rather than falling in, is hurled back outward along the axis of rotation in a tightly focused jet, accelerated to very nearly the speed of light, blasted out into the galaxy in a beam that can stretch for thousands of light years, far longer than the distance between the Sun and most of the stars you can see. M87's jet extends some 5,000 light years out from the core, a searchlight of energy fired by the black hole's spin and the infalling matter, carving through the galaxy. These jets are how some black holes announce themselves across the entire universe, and when one happens to be pointed directly at the Earth, we see the object blaze with an intensity that once baffled astronomers completely. The same object that is darkest at its centre, that swallows everything, is also capable of firing out one of the brightest and most far-reaching beacons in all of creation. The black hole gives off no light. The matter falling into it and the spin twisting around it can light up a galaxy. There is something worth sitting with here, in the quiet, about what these images actually represent. For all of human history before 2019, no one had ever seen a black hole. They were creatures of mathematics and inference, known by their effects, photographed only as paintings and simulations, objects we were confident existed but had never laid eyes on. And then, within the lifetime of most people listening to this, that changed forever. We crossed a line that can never be uncrossed. We are now a species that has seen the edge of the abyss directly, that has photographs of the boundary past which the universe keeps its secrets, that has turned its own planet into an eye and looked into the dark and found exactly what the equations promised would be there. Carl Schwarzschild, dying in that field hospital, working out the size of the boundary, could never have imagined that a little more than 100 years later his descendants would point the whole Earth at the sky and take its picture. The thing he found in the abstract, we have now found in the concrete. The door is real, we have seen its frame, and yet, as monstrous as M87's 6.5 billion solar mass black hole is, as much as it dwarfs the giant at the centre of our own galaxy, it is still not the largest type. There are black holes out there that make even M87 look modest, objects so far beyond the scale of anything we have discussed that they seem to push against the very limits of what the universe should be able to assemble. They are not just supermassive. Astronomers have started reaching for a new word for them, because the old word no longer feels big enough. To meet them, we have to leave the local universe behind entirely and travel to some of the most distant, most luminous, most extreme objects ever detected, the ones that shine across nearly the entire observable cosmos, powered by the hungriest hearts that exist. Part 7. The ones that break the scale. There is a class of black hole so large that the word supermassive begins to feel inadequate, and astronomers have started using a heavier word for them. Ultramassive. These are the black holes whose mass climbs into the tens of billions of suns, objects so enormous that they sit at the absolute limit of what we understand black holes to be able to become. To meet the most famous of them, we have to travel a distance that is genuinely difficult to hold in the mind, and we have to understand a peculiar fact about looking deep into space, which is that to look far away is always to look far back in time. When you see a distant object in the sky, you're not seeing it as it is now. You're seeing the light that left it long ago, light that has been travelling toward you for as long as the distance demands. Look at the sun, and you see it as it was 8 minutes ago. Look at the nearest star, and you see it as it was 4 years ago. And look at the object we are about to discuss, and you are seeing it as it was more than 10 billion years ago, when the universe itself was young, only a few billion years old, long before the Earth or the Sun had formed. The light has been crossing the dark for most of the entire history of the cosmos to reach you. It carries a portrait of an ancient time. The object is called TON 618, a name it inherited from a survey conducted at an observatory in Mexico back in 1957, when it was first catalogued as nothing more than a faint blue point of light, mistaken at the time for an ordinary star. It is anything but ordinary. TON 618 is a quasar, which is the name we give to a supermassive black hole that is feeding so ferociously that the material falling into it blazes with the light of trillions of suns, outshining the entire galaxy around it, sometimes outshining hundreds of galaxies, visible across nearly the whole observable universe. When quasars were first discovered, in the early 1960s, they made no sense at all. Astronomers found these intense points of light that looked almost like ordinary stars, and yet their light was stretched in a way that meant they were extraordinarily far away, billions of light years distant, and for something that far away to appear that bright, it had to be releasing an almost inconceivable amount of energy. Worse, the brightness of some of them flickered over days or weeks, which meant the source had to be small, no larger than a few light days across, because nothing can change in brightness faster than light can cross it. So here was the puzzle, something smaller than our solar system, pouring out more light than an entire galaxy of hundreds of billions of stars. No ordinary process could do that. Not fusion, not the burning of stars, nothing in the familiar catalogue of how the universe makes light. It took years for astronomers to accept the only answer that worked. The power source was matter falling into a supermassive black hole. As gas spirals inward and is squeezed and heated to millions of degrees, it converts a portion of its mass directly into radiation, and it does so with an efficiency far beyond anything else in nature, far beyond the fusion that powers the stars, releasing a staggering fraction of the infalling matter's mass as pure light. The darkest objects in the universe turned out to power the brightest. The thing from which no light escapes turned out to be the engine behind the most luminous objects ever seen. That is the strange double nature of the giants, and TON 618 is the extreme of it, a black hole so vast and once so hungry that its feeding outshone nearly everything. The light you would see from TON 618 is not the black hole itself, which remains as dark as any other. It is the unimaginable glow of matter being torn apart and superheated in the swirling disk around it as it spirals in, and from the properties of that light, from the violence of the gas whipping around the central object, astronomers have weighed the black hole at the heart of TON 618 and arrived at a number that strains belief, somewhere in the range of 40 to 66 billion times the mass of the Sun. Sit with that figure for a moment, because it is almost impossible to feel its true size. We have come a long way in this journey. We started with stellar mass black holes of a few dozen suns. We met the giant at the centre of our galaxy, 4 million suns, and that already seemed enormous. We met the monster in M87, 6.5 billion suns, large enough to swallow our entire solar system within its event horizon, and TON 618 is roughly 10 times more massive even than that. Its event horizon would not merely contain our solar system, it would dwarf it many times over. If you placed it where our Sun is, its shadow would extend far beyond the most distant planets, far beyond the edge of the planetary realm, a sphere of darkness so vast that a beam of light, travelling at the only speed light knows, would need weeks to cross from one side to the other. There is nothing in human experience to compare it to. It is a single object, a single point of collapsed mass, that is larger across than many entire star systems, holding the mass of a substantial fraction of a small galaxy, compressed behind a boundary from which nothing returns. And TON 618 may not even be the largest. There is another contender, the black hole at the centre of a distant galaxy cluster called the Phoenix Cluster, an object sometimes called Phoenix A, whose mass has been estimated by some methods as high as 100 billion suns. though that figure is far less certain and rests on more indirect reasoning than the measurement of Ton 618. There is an ultra-massive giant lurking in a galaxy known by the catalogue name Abel 1201, weighed not by its glow, but by the way its gravity bends the light of objects behind it, a technique that turns the black hole's own warping of space into a scale. There are others scattered across the deep universe, each one a candidate for the title of largest, each one pushing at the edge of what seems possible. We are no longer talking about objects. We are talking about something closer to cosmic landmarks, anchors so massive that they shape the formation of the galaxies and clusters around them. All of which raises a question that scientists have genuinely begun to investigate in recent years, a question that sounds almost childlike in its directness, and yet leads somewhere profound. Is there a limit? Can a black hole simply keep growing forever, swallowing more and more, climbing endlessly toward larger and larger masses, or is there some ceiling, some maximum size beyond which nature will not let them go? A team of astronomers led by Priyamvada Natarajan at Yale has explored exactly this, and their reasoning is elegant. A black hole grows by feeding, by pulling in surrounding gas. But the act of feeding produces tremendous radiation, the brilliant glow of the heated in falling matter, and that radiation pushes outward on the surrounding gas, blowing it away, cutting off the supply. The bigger the black hole gets, the more fiercely it shines when it feeds, and the more effectively it clears out its own neighbourhood, choking off its own food. There is, in this picture, a kind of natural self-regulation, a point at which the black hole becomes so large and so bright that it can no longer easily grow, having scattered away everything it might have eaten. Their estimates for that ceiling land in the same neighbourhood as the largest black holes we actually observe, somewhere in the tens of billions of solar masses, which is a tantalising hint. It suggests that the giants, like TON 618, may not be unusual outliers at all, but rather examples of black holes that have grown about as large as the universe will allow, having reached the limit and stopped. We may, in other words, have already discovered black holes near the absolute maximum size that can exist. There is a strange comfort in that idea, and a strange awe. The comfort is that the universe has limits, that even its most extreme objects obey rules, that the runaway growth of these monsters is checked by the very brilliance of their own feeding. The awe is in realizing what those limits actually are. The ceiling, if it exists, is tens of billions of suns. The universe permits the assembly of single objects that massive allows mass to gather and collapse and concentrate to that degree, and then, only then, says no further. We are not looking at small things bumping against a low boundary. We are looking at the largest objects the cosmos can build, finished, complete, having grown to the edge of the possible and gone quiet. Most of these ultramassive giants, like the largest in M87, are relatively calm now. The fierce quasar phase, the blazing period of voracious feeding that made TON 618 visible across the universe, is something that happened long ago in the early cosmos, when galaxies were rich with gas and the black holes at their centres were gorging. The universe of today, the local universe, is a quieter place, its great black holes mostly fed down to slow, gentle accretion or near dormancy, sleeping giants like the one at the centre of our own galaxy. When we look at Ton 618 blazing, we are looking at the distant past, at an epoch of feeding that has long since ended. The actual Ton 618, as it exists now, billions of years after the light we see departed, has almost certainly quieted, grown calmer, finished its great meal. We are watching a recording of a feast that is already over, the light of a younger, hungrier universe still arriving at our telescopes long after the meal itself has ended. And this connects to one of the deepest and most unsettling puzzles in all of modern astronomy, a puzzle that has only sharpened in recent years as our instruments have grown more powerful and have begun to peer into the very earliest epochs of the universe. The largest black holes we see in the distant ancient cosmos, the quasars blazing in the young universe, are far too large to have formed by any process we understand in the short time available to them. They are like finding a fully grown adult only moments after birth. To grow a black hole to billions of solar masses takes time, a great deal of time, even feeding at the maximum possible rate. And yet there they are, the giants, already enormous, in a universe that had barely begun. How did they get so big so fast? That question has haunted astronomers for years, and recently with a new and extraordinary telescope peering deeper into the early universe than anything before it, the puzzle has not been resolved. It has become stranger, because that telescope has found things in the infant cosmos that, frankly, no one fully expected and no one can yet fully explain. Part 8. Too big, too soon. In the summer of 2022, a new eye opened in space. The James Webb Space Telescope, parked far beyond the Moon, at a quiet gravitational balance point, began returning images of a depth and clarity that no instrument before it had ever achieved. It was built, among other purposes, to look back in time, to capture light so ancient and so stretched by the expansion of the universe that it had shifted out of the visible range entirely into the infrared, light from the first few 100 million years after the beginning, from the era astronomers call the cosmic dawn. And almost immediately the telescope began finding things that did not fit. Small, intensely red points of light scattered through the early universe, far more numerous than anyone had predicted, appearing at a time when the cosmos was only a few 100 million years old. The astronomers, casting around for a name, called them the little red dots. At first, no one knew what they were. They were too small and too compact to be ordinary galaxies, too red and too bright in strange combinations, and they appeared in the early universe, and then largely faded away again less than 1 billion years later. A population that flared into existence near the beginning, and then mostly vanished, like a generation of objects that belonged to one brief era and no other. They looked like nothing seen before. And as astronomers studied them through the following years, gathering their light, splitting it into spectra, reading the fingerprints of the gas within them, a startling answer began to emerge. The little red dots are not really galaxies in the way we usually mean. At the heart of many of them sits a supermassive black hole, feeding, surrounded by a thick cocoon of dense gas. The whole object dominated not by stars but by the glow of matter, falling into the black hole at its centre. Some astronomers have begun calling them by an even stranger name, black hole stars, because in a sense each one behaves almost like a single enormous object, a black hole wrapped in so much gas that the gas itself glows like the atmosphere of a star. The black hole hidden deep inside the warm shroud it is devouring. And these early black holes are far too large for the age of the universe in which we find them. That is the heart of the puzzle, and it has only deepened the longer we have looked. In August of 2025, astronomers announced that they had confirmed the earliest black hole yet found at the centre of one of these little red dots, a galaxy given the name CAPES-LRD-Z9. Its light left it when the universe was only about 500 million years old, which is to say we're seeing it as it existed in the first 4% of cosmic history. And already, that early, that close to the beginning, it held a black hole with a mass of roughly 300 million suns. 300 million solar masses fully assembled, blazing, when the universe had barely had time to make its first generations of stars. By every model we have of how black holes grow, this should not be possible. There simply was not enough time. You cannot grow a black hole that large that fast by ordinary feeding, not from the small seeds that dying stars provide. The numbers do not add up, and yet there it is, observed, confirmed, real, existing in defiance of our expectations at the very edge of the visible past. So how did they form? This is one of the genuinely open and actively argued questions at the frontier of astronomy right now, and there is no settled answer, only competing ideas and the honest acknowledgement that we do not yet fully understand. One possibility is that these early giants grew at the absolute theoretical maximum rate, feeding so furiously, so continuously, that they climbed to enormous masses in record time, force-fed by the thick envelopes of gas surrounding them. Another possibility, and one that has gained ground, is that they did not start from small stellar seeds at all. Instead of beginning as the few dozen solar mass remnant of a single dying star, and then growing slowly, perhaps they began as much heavier seeds, formed when an enormous cloud of gas in the early universe collapsed directly into a black hole all at once, skipping the star stage entirely, producing a seed of 10,000 or 100,000 solar masses from the very start. This idea, called direct collapse, would give the early black holes a tremendous head start, a running leap toward the giant masses we observe. Both ideas are being tested against the new observations, and the data does not yet cleanly favour one over the other. We are right now in the middle of working it out, and the answer, when it comes, will reshape our understanding of how the largest objects in the universe came to be. There is something humbling in this, and I want to dwell on it for a moment as you rest, because it is easy to come away from a journey like this thinking that science has it all figured out, that the catalogue is complete and the questions answered. It is not, and they are not. Here, at the deepest reach of our most powerful telescope, looking back at the dawn of everything, we have found objects we did not predict, behaving in ways we cannot yet fully explain, and the experts, the people who have devoted their lives to this, will tell you plainly that they are still arguing about it, still gathering data, still revising their models. The little red dots arrived as a genuine surprise, and surprises in science are not failures. They are the most valuable thing there is, the signal that the universe is larger and stranger than our current picture of it, the invitation to learn something new. We thought we understood how black holes grow. The early universe is telling us, gently but unmistakably, that we do not completely, not yet. These ancient giants also do something more than feed quietly. Sometimes a star wanders too close to a black hole and is torn apart, stretched and shredded by the difference in gravity between its near side and its far side, ripped into a long stream of gas that wraps around the black hole and is slowly consumed. Astronomers call this a tidal disruption event, and in recent years they have caught these stellar killings in the act, watching the sudden flare as a black hole swallows a star that strayed within reach. One such event, recorded fairly recently, has been ongoing for an unusually long time, the black hole apparently still working its way through the remains of the unfortunate star, a process one astronomer memorably described as being like a fish only halfway down the whale's gullet, still visibly being swallowed, the meal not yet complete. There is a quiet drama in that image, a star that lived for perhaps billions of years, that may have warmed worlds of its own, undone in a slow gravitational unravelling, its substance spiralling down into a darkness that will keep no memory of it at all. And that, in the end, is what every type of black hole shares, from the smallest stellar remnant to the largest ultramassive giant to these strange early monsters in their red cocoons. They keep nothing. Whatever falls in is gone, its details erased, its information swallowed behind a boundary that the rest of the universe can never look past. A star, a planet, a cloud of gas, anything at all, once across the event horizon, becomes simply mass, adding to the total, contributing to the size, but losing everything that made it what it was. The black hole does not remember the star it ate any more than the sea remembers the rivers that fed it. It only grows a little larger, a little heavier, and goes on. We have now travelled from the small to the enormous, from the workhorses to the giants, to the impossible early monsters at the edge of time. We have gone as large and as far and as ancient as the family reaches, and so it would seem natural to stop here, at the summit, having met the largest things the universe can make. But the family is not finished. There is another branch entirely, a category that runs in the opposite direction, away from the enormous and down toward the unimaginably small. These are the black holes that may have been born not from stars, not from collapsing gas clouds in galaxies, but in the first fraction of the first second of the universe itself, in the chaos immediately after the beginning. They could be as light as a mountain or as small as an atom. They might make up a large fraction of all the unseen matter in the cosmos. And unlike every other type we have discussed, the strangest of them might not be far away at all. To meet them, we have to leave the realm of the seen entirely, and step into the realm of the possible, the predicted, the not yet found. We are going to talk about the black holes you cannot see. Part 9, the ones you cannot see. Everything we have discussed so far, every type of black hole from the stellar remnant to the ultramassive giant, has one thing in common. It was born from the death or collapse of something large. A star ran out of fuel. A cloud of gas fell together. Matter that already existed in great quantity gathered and crushed itself down. But there may be another kind entirely, a kind that did not need a star or a gas cloud or any of the slow machinery of the cosmos to make it. A kind that was born in the first instant of the universe, in the fraction of a second after the beginning, when everything was hot and dense and chaotic beyond imagining. These are the primordial black holes, and they are at this moment entirely theoretical. We have never confirmed a single one. And yet the idea of them, first proposed by Stephen Hawking and others more than 50 years ago, refuses to go away, because it would explain so much, and because we cannot yet rule it out. Here is the reasoning, and it is beautiful in its simplicity. To make an ordinary black hole, you need a lot of mass gathered in one place, because under normal conditions matter is spread thin, and gravity is weak, and you need something dramatic like a dying star to force a collapse. But in the very first moments after the beginning, the universe was not spread thin. It was almost unimaginably dense, every region packed with energy, the whole cosmos a churning sea of extreme conditions. And in that environment, you would not need a star's worth of mass to make a black hole. You would only need a region that happened to be slightly denser than its surroundings, a ripple in the primordial chaos, a place where the energy clumped a little more than elsewhere. If such a clump were dense enough, it could collapse directly into a black hole, then and there in the first second, without any star, without any of the usual ingredients. And crucially, because the amounts involved could be almost anything, these primordial black holes could come in any size at all, not just the few dozen solar masses that dying stars produce, but a continuous range stretching far below and far above. Some could be as massive as a mountain, some as small as an atom, some smaller still. Think about what that means physically. A black hole with the mass of a large mountain, several billion tons, would have an event horizon smaller than a single atom. A black hole with the mass of the entire Earth, as we discussed at the very beginning, would be the size of a marble, less than a centimetre across. These primordial black holes, if they exist, would be tiny, dense, dark points scattered through space, far too small to see, far too small to photograph, emitting essentially no light, betraying themselves through almost nothing. And there is a reason astronomers have not given up on them despite never finding one, a reason that has kept the idea alive for half a century. The universe contains a vast amount of matter that we cannot see, that gives off no light, that we know is there only because of its gravity, holding galaxies together and bending the paths of light. We call it dark matter, and we do not know what it is made of, and one of the longest-standing candidate explanations for at least some of that invisible matter is that it might be made of primordial black holes, countless tiny black holes left over from the first second, drifting through every galaxy, unseen, unfelt, except in their collective gravitational pull. If that were true, then a significant fraction of all the matter in the universe would be made of objects we have never directly detected. Black holes so small and so dark that they hide in plain sight, woven invisibly through every structure in the cosmos. Now, scientists have worked hard to test this idea, and it is important to be honest about where things stand, because the search has narrowed the possibilities without closing them. Across many ranges of possible mass, primordial black holes have been largely ruled out as the main component of dark matter, because if they existed in those ranges and in those numbers, we would have noticed their effects, the way they would bend light or disrupt stars or leave other fingerprints. But there remain windows, particular ranges of mass, where they have not been excluded, where they could still exist in great numbers and account for the dark matter, and we simply do not yet have the means to confirm or deny it. So the primordial black hole sits in a strange position in the family, the only member that is purely hypothetical, the only one we have never seen, and yet a member that could, if it is real, turn out to be the most numerous of all, outnumbering every star and every other type of black hole combined, the silent dark majority of the universe's matter. And here we arrive at the strangest property of all, the one that ties the smallest black holes to the largest, and reveals something no one expected before Hawking worked it out. For most of the history of the idea, black holes were thought to be perfectly, eternally black, objects that only grew, that only swallowed, that could never give anything back. Hawking proved otherwise. Drawing on the deepest available understanding of how empty space behaves at the smallest scales, he showed that black holes are not perfectly black at all. They glow, very faintly, with a kind of radiation that now bears his name, Hawking radiation. Through a subtle process at the very edge of the event horizon, a black hole slowly leaks energy out into the universe, slowly loses mass, slowly evaporates, and the smaller the black hole, the faster it does this. The giants, like Ton 618, evaporate so slowly that the timescale is beyond all meaning, far longer than the current age of the universe multiplied many times over. But a tiny primordial black hole, a small one, would evaporate much faster, glowing more and more brightly as it shrinks, shrinking faster as it glows, until in its final moments it would vanish in a sudden brilliant burst of energy, a final flash as the last of it converted to radiation, and the black hole simply ceased to be. If primordial black holes of the right small size exist, then some of them should be reaching the end of their lives right now, somewhere in the universe, ending in these tiny bright explosions, and astronomers have searched for exactly that signature, those final flashes, as a way to prove the whole idea. So far the sky has been quiet, but the search continues. This brings us to the thought I promised you at the very beginning, the one I told you to stay for, and I want you to hold it gently rather than let it frighten you, because the truth of it is far more wonderful than it is alarming. If primordial black holes exist in the smallest ranges, then they are out there now, drifting through the galaxy, passing through regions of space at great speed, and the very small ones would be so tiny and so dark that one could pass through ordinary matter and leave almost no trace. One could, in principle, pass through a planet. One could pass through a room. One could pass through you, in through one side and out the other, in a fraction of a second, and you would feel nothing, see nothing, know nothing, because an object the size of an atom moving through the loose, mostly empty space of your body would almost certainly touch nothing at all. The atoms of you being themselves mostly empty space. The strangest member of the black hole family, if it is real, is not a distant monster at the centre of some far galaxy. It is potentially the most common type in existence, the smallest, the darkest, the one we have never seen, the one that could be threaded invisibly through the very ground you are resting on, through the air you are breathing, perhaps, on the rarest of occasions, through you. Not as a threat, not as a danger lurking, just as a quiet possibility, a category of object the universe may have made in unimaginable numbers in its first instant, and then scattered everywhere, harmless and unseen, hiding in the empty spaces of everything. It is worth saying clearly, because the human mind likes to turn the unknown into fear, that there is no danger here. Even if such objects exist and one passed through the Earth, the effect would be undetectable, the chance of it ever causing harm so vanishingly small as to be meaningless. There was once a public worry that scientists building powerful particle colliders might accidentally create tiny black holes that would swallow the Earth, and it is worth knowing that the fear was unfounded, that any such micro-black hole would, by Hawking's own physics, evaporate instantly, and that the universe has been bombarding the Earth with far higher energy collisions from space for billions of years without incident. The smallest black holes, if they exist, are not the end of the world. They are the opposite of dramatic. They are the universe's quietest possible secret, a thing so small and so dark that its entire existence might be to drift, unnoticed, through everything that is, forever, or until it flickers out in a tiny flash that no one ever sees. So now we have the whole family, the entire range, from the smallest hypothetical points born in the first second to the largest ultra-massive giants pressing against the limits of the possible. We have met every type, and there is one last thing to understand about all of them, a fate they all share, a destination at the end of the longest road there is. Because the universe is not static, it is changing, aging, moving slowly toward a future so distant it makes everything we have discussed seem to have happened only moments ago. And in that deep future, in the final eras of the cosmos, the black holes are not bystanders. They are the main characters. They are, in a very real sense, the last things that will exist. Before we come to rest, let us go all the way to the end and see what becomes of the family when everything else is gone. Part 10. The last things in the universe. The universe is young. That is a difficult thing to feel because 13.8 billion years sounds like an eternity, and against the span of a human life it is. But against the future that is coming, the true future, the full lifespan of the cosmos, the universe has barely begun. We live in what astronomers sometimes call the stelliferous era, the age of stars, the brief bright morning of the universe when galaxies are full of burning suns and the night sky is scattered with light. It feels permanent. It is not. It is a phase, a chapter, and like every chapter it will end, and what comes after is a story in which the black holes we have spent this whole journey meeting become the central characters, the inheritors, the last structures standing in an emptying cosmos. Begin with the stars, because the stars come first. Right now, across the universe, new stars are being born from clouds of gas, as they have been for billions of years. But the supply of gas is finite, and slowly, over enormous spans of time, it is being used up, locked away in dead stars and black holes, no longer available to make new ones. Eventually, in something like 100 trillion years, the gas will run too thin, and the last star will form. After that, no new stars. New. The existing stars will live out their lives and die, one by one, the largest first and the smallest last. The small, cool, frugal stars, the red dwarfs, will burn on for trillions of years more, the final embers of the age of light, but even they will fade. And then, in a universe perhaps 100 trillion years old, the last star will flicker out, and the cosmos will go dark. The age of stars will be over. The sky, if there were anyone left to look at it, would be empty of suns. What remains, in that long darkness, is the wreckage. The cold dead cores of stars, the white dwarfs slowly fading to black, the neutron stars, the drifting planets long since frozen, and the black holes. All the black holes that have ever formed, the stellar remnants and the intermediate ones and the supermassive giants at the centres of galaxies, all still there, all still dark, now the most massive and most significant objects in a universe that has lost its light. Astronomers call this coming age the degenerate era, and then the black hole era, and the names tell the story. The black holes inherit the universe. They are the heaviest things, the most enduring things, the gravitational anchors around which the cold debris still slowly turns. For an almost unimaginable span of time, far longer than the entire age of stars that preceded it, the universe will be a place of darkness ruled by black holes, their numbers slowly growing as the last remnants of matter fall into them, and as they merge with one another, the giants at the galactic centres swelling as everything around them eventually drains inward or drifts away. And then, slowly, so slowly that the word slowly loses all meaning, even the black holes begin to die. This is the final consequence of what Hawking discovered. The faint glow, the leaking of energy, the inexorable evaporation. We said that the smallest black holes evaporate fastest, and the largest evaporate slowest. And now we reach the largest, the supermassive giants, the TON 618s of the cosmos, and we ask how long they will last. The answer is a number so large it cannot be felt, only written. A black hole the mass of the Sun would take something like 10 followed by 67 zeros years to fully evaporate. A supermassive giant would take 10 followed by perhaps 100 zeros. These are not numbers you can hold in your mind. They dwarf the current age of the universe so completely that the entire 13.8 billion years we have lived through so far, the whole history of stars and galaxies and life and everything that has ever happened, rounds away to nothing against them. A single grain of sand against every beach on Earth, and then far, far more. But the number, however vast, is finite. The black holes do not last forever. They glow faintly, for that almost endless span, leaking their mass away one whisper of radiation at a time, shrinking with infinite patience across an ocean of years. And in the very, very end, each black hole, having shrunk small enough, accelerates toward its finish. As it loses mass, it glows brighter, and glowing brighter, it loses mass faster, until in its final moment, after all those uncountable years of patient darkness, it flares in a last burst of radiation and is gone. The largest objects the universe ever made, the giants that anchored galaxies, that swallowed stars whole, that bent light around themselves and erased everything that fell within them, end exactly as the smallest primordial black holes would, in a final flash and then nothing. One by one, across spans of time that make the age of stars look like a single heartbeat, the black holes wink out. And when the last one goes, when the final black hole in the entire cosmos releases its last burst of energy and ceases to exist, the universe enters its true and final state. The dark era, a cold, thin, expanding emptiness, populated only by the faint and ever-cooling glow of scattered radiation, drifting apart forever, with no structure left, no stars, no black holes, nothing but the slow dilution of the last light into an endless dark. There is a way to feel this that is unbearably bleak, and there is a way to feel it that is something closer to peace, and on a night like this, drifting towards sleep, I would offer you the second. Because what this deep future tells us is not really about emptiness. It is about how astonishingly improbably rich the present is. We do not live in the dark era. We do not live in the long cold reign of the black holes. We live in the morning, the brief bright morning of the universe, when there are still stars, still galaxies full of light, still gas forming new suns, still the whole machinery of the cosmos running and warm and full. The black holes that will one day inherit everything are, for now, the exceptions, the rare dark points scattered through a universe that is otherwise blazing with light. We arrived early. We arrived during the part of the story with the most happening in it, the most light, the most possibility. Out of all the eras the universe will pass through, almost all of which are dark and cold and slow beyond comprehension, we exist in the rare, fleeting, luminous beginning. That is not a small thing. That is perhaps the least small thing there is. And the black holes themselves, when you hold them against this immense backdrop, stop seeming like monsters and start seeming like something else. They are not villains in the story of the universe. They are its bones, its anchors, its most patient and enduring structures, the objects that will outlast the stars and the galaxies and everything we have ever called bright, and that will, in the fullness of time, even outlast themselves, departing at the very end in their quiet final flashes. They are how the universe holds itself together in the age of light, and they are how it slowly winds down in the age of dark. The same simple recipe that Schwarzschild found in his field hospital, mass-crushed small enough to close a door in space, plays out across every scale from the atom to the galaxy, and across every era from the first second to the last, the unifying thread that runs through the entire life of the cosmos, beginning to end. We have met every type now, the whole family, from the stellar remnants salted through our galaxy, to the ultramassive titans at the edge of the possible, to the hypothetical primordial points that may thread invisibly through everything. We have seen how they are born, how they live, and how, in the end, even they will quietly die. But there is one thing we have only ever described from the outside, one experience that no telescope will ever capture, and no instrument will ever record, because it lies on the far side of the only true one-way door in the universe. Every type of black hole, large or small, ancient or newborn, shares it, the crossing, the moment of going in. Before we gather the whole family together one final time and let it all go, let us do the one thing we have not yet done. Let us imagine gently, from the safety of the warm and lighted present, what it would be to fall into one of these things, and what the universe would look like as we went. Part 11. What it would be to fall in. Imagine choosing one. Not a small one, not a hypothetical primordial point, but a true supermassive giant, one of the calm ones, like the 4 million solar mass anchor at the centre of our own galaxy, or something larger still. You are in a ship drifting toward it, and ahead of you is the dark, growing larger, and around its edge the faint distorted glow of distant stars whose light is being bent and smeared by the warping of space. There is no surface ahead. There is no wall. There is only the boundary, the event horizon, an edge in empty space that you cannot see directly because it gives off nothing, marked only by the strange behaviour of the light passing near it. And the first surprising thing, the thing that contradicts almost every instinct, is that for a giant black hole, crossing that boundary would be utterly gentle. You would feel nothing at all. This is one of the most counterintuitive truths in all of physics, and it is worth letting it unwind slowly. We tend to imagine that approaching a black hole means being torn apart by violent gravity, and for a small black hole that is true. The danger is not the strength of gravity itself, but the difference in gravity across your body. The fact that the pull on your feet would be stronger than the pull on your head if you fell in feet first, stretching you. Physicists have a vivid and slightly absurd word for the result: spaghettification. Near a small stellar mass black hole, that difference becomes lethal long before you reach the horizon, stretching you into a thin stream of matter, drawn out like pulled candy, undone atom by atom. But the larger the black hole, the gentler that difference becomes at the horizon, because the horizon is so much farther from the centre. For a truly supermassive giant, you could cross the event horizon, pass through the boundary of no return, and feel nothing whatsoever. No stretching, no force, no sign that anything had changed. The universe outside would still be visible behind you. You would not know you had crossed, and yet you would have. The door would have closed silently, and every possible path now would lead inward, and you would simply not have felt it happen. The most absolute event imaginable, the crossing into a region from which nothing can ever return, would arrive without any sensation at all. There is a strange economy to what a black hole actually is, and it is worth understanding before we go further, because it reveals one more way the family can be sorted. We have spent this whole journey classifying black holes by their mass, from the smallest to the largest, and mass is indeed the most important property. But it is not the only one. According to the theory, a black hole can have exactly 3 properties, and only 3, no matter what fell in to make it: its mass, its spin, meaning how fast it rotates, and its electric charge. That is all. Everything else, every detail of every star and cloud and world that ever fell in, is erased, leaving behind only those 3 numbers. Physicists gave this idea a memorable name. They say that a black hole has no hair, meaning it has no other features, no individuality, no memory of its origins beyond mass and spin and charge. 2 black holes with the same mass, the same spin, and the same charge would be, as far as the universe is concerned, perfectly identical, indistinguishable, even if one was built from stars and the other from an entire galaxy of swallowed light. The black hole forgets. It keeps only those 3 numbers and discards the rest. In practice, charge hardly matters, because the universe is electrically balanced and any charged black hole would quickly pull in opposite charges and neutralize itself. So the real classification, beyond mass, comes down to spin, and almost every black hole in the universe spins, often ferociously, because the matter that formed it was rotating, and that rotation has nowhere to go but inward as the matter collapses, spinning faster and faster as it shrinks, the way a skater pulls in their arms and accelerates. A non-rotating black hole, the simple kind that Schwarzschild first described, is really only a textbook idealization. The real ones, the ones at the centers of galaxies, the ones born from collapsing stars, are spinning so fast that their outer edges may be moving at a large fraction of the speed of light. And a spinning black hole does something to the space around it that a still one does not. It drags space itself into rotation, twisting the fabric of the cosmos around with it, so that near a spinning black hole nothing can possibly stay still. Everything is forced to turn in the direction the black hole turns, caught in a whirlpool not of matter but of space. A region where standing still is not merely difficult but physically impossible, where the dragging of space itself sweeps you along. There is even a way, in principle, to steal energy from a spinning black hole by dropping something into that whirling region and letting it fling part of itself back out, faster than it went in, carrying away a sliver of the black hole's rotation. The universe's most absolute objects can, in this one strange way, be made to give something back, to spin a little slower in exchange for a little borrowed speed. Now consider what someone watching you from outside would see, because this is where time itself begins to behave strangely, and it is one of the loveliest and eeriest consequences of the whole theory. As you fall toward the horizon, the immense gravity slows down time for you, relative to the distant watcher, not in a way you would notice. Your watch would tick normally to you, your thoughts would run at their usual pace, but to the observer far away your time would appear to run slower and slower as you approach the boundary. They would see you falling more and more slowly, your motion stretching out, your image growing redder and dimmer as the light you sent back was stretched by the climb out of the gravitational well. And in their reckoning, you would never quite cross. You would seem to slow and freeze, hovering just at the edge, fading toward darkness, your final image stretched out across an eternity of their time, a frozen, reddening ghost that never quite reaches the boundary and never quite disappears. From your point of view, you sailed straight through in a moment. From theirs, you hung at the threshold forever, growing dimmer, never arriving. Both are true. There is no single answer to the question of when you crossed, because time near a black hole is not one shared river, but something that bends and stretches differently depending on where you stand. And once you are inside, what then? Here we reach the true edge of knowledge, the place where even the equations begin to fail. Inside the horizon, as we said at the very beginning, the center is not a place but a time, an unavoidable future toward which everything falls. At that center, the mathematics predicts a singularity, a point where the density becomes infinite, where the curvature of space becomes infinite, where the theory that brought us all this way, the theory Einstein built and Schwarzschild solved, simply breaks down and stops giving sensible answers. We do not actually know what is at the centre of a black hole. We know what our best theory says, and our best theory says that at the centre it can no longer describe what happens. A singularity is not really an object. It is a confession, a place where physics throws up its hands and admits that something is missing, that there must be a deeper theory we do not yet possess, a marriage of gravity and the quantum world that no one has yet completed. Whatever is truly at the centre of every black hole in this entire family, from the smallest to the largest, is genuinely unknown, hidden not only by the horizon, but by the limits of our own understanding. It is one of the great unsolved problems in all of science, and it sits at the heart, quite literally, of every object we have discussed tonight. There is a related mystery, just as deep, that has occupied some of the finest minds of the last half-century, and it concerns not what is inside, but what becomes of everything that falls in. Remember Hawking radiation, the faint glow by which black holes slowly evaporate. The radiation that comes out seems to carry no information about what went in. A book and a brick and a star, if they had the same mass, would all produce the same featureless glow as the black hole that ate them slowly evaporated away. So when the black hole finally vanishes in its last flash, what happened to all the detail, all the information, all the specific arrangement of everything it ever swallowed? Did it simply cease to exist, erased from the universe entirely? The laws of physics, at their deepest level, are not supposed to allow that. Information is not supposed to be truly destroyable, and yet a black hole seems to do exactly that, to swallow the world's details and then quietly evaporate, leaving no record. This is the information paradox, and physicists have argued about it for decades, proposing that the information is somehow subtly encoded in the radiation, or smeared across the horizon, or preserved in ways we do not yet grasp. There is no fully settled answer. It remains one of the sharpest open questions in theoretical physics, a puzzle that links the largest objects in the cosmos to the deepest rules of reality, and it is still, right now, unresolved, still being worked on, still waiting for whoever will finally see clearly what the rest of us cannot. I tell you these unsolved things not to leave you uneasy, but to leave you with the right feeling, which is wonder rather than certainty. It would be a smaller and less honest story if I told you that we understand black holes completely, that the family's fully catalogued and the questions all answered. The truth is richer than that. We have come an extraordinary distance, from a dying man's calculations in a field hospital to photographs of the abyss taken by a telescope the size of the Earth. And along the way we have learned to weigh the unseen and to hear the collisions of giants across 1 billion years of darkness. And still, at the centre of every one of these objects there is a question mark. Still, in the glow of their slow evaporation, there is a mystery no one has solved. The black hole is not a closed book. It is the open frontier, the place where what we know meets what we do not, and that meeting place is, if you let it be, one of the most beautiful things in all of science. To stand at the edge of the known and feel how much is still dark is not a failure. It is the privilege of being alive in a universe far larger than any single mind can hold. So we have fallen in imagination, and crossed the silent boundary, and watched our own image freeze behind us, and approach the centre where knowledge itself runs out. And now it is time to come back, back from the edge, back from the deep future, back from the dawn of time, back across the whole enormous family, all the way to here, to the warm dark room, to the weight of your own body resting, to the slow rhythm of your breath. Let us gather it all together, one last time, and then let it go, and let you go with it, gently into sleep. Part 12. Everything in its place. Let the whole family pass before you one last time, slowly, like a procession seen from far away, and let each one settle into its place in the order of things. There is a star somewhere in our galaxy that ran out of fuel and could not hold itself up, and in the violence of its death it left behind a small dark point, a few dozen kilometers across, heavier than the sun, and it drifts now through the dark between the stars, one of hundreds of millions, silent, invisible, asking nothing of anyone. That is the stellar mass black hole, the workhorse, the most ordinary member of the family, and the nearest one to you is closer than most of the stars you can name. There is a pair of them, somewhere far away, that finished their long death spiral more than 1 billion years ago and sent a single rising note out into space, a note that washed over the Earth in the same century we finally built the instruments to feel it. That is the gravitational wave, the first thing we ever heard from a black hole, the proof that they are real, arriving exactly when we became able to notice. There is a black hole in the awkward middle, neither small nor enormous, hiding in the heart of some old cluster of stars glimpsed only recently, still half mysterious, still argued over, the missing link that may explain how all the giants came to be. There is, at the centre of our own galaxy, 26,000 light-years away, hidden behind a wall of dust, a giant of 4 million suns, and you are orbiting it right now, have been your whole life, will be until you die, on a journey that takes 200 million years to complete a single lap. There is the first one we ever photographed. 6.5 billion suns at the heart of a distant galaxy, large enough to swallow our whole solar system, its dark shadow ringed in orange light that has been bent around the back of the abyss and brought into view by the curving of space itself. There are the ultramassive titans, the TON 618s, tens of billions of suns, shadows so vast that light needs weeks to cross them, pressing against the very limit of how large the universe will allow a single object to grow. There are the impossible early monsters, the black holes at the dawn of time, already enormous when the universe was barely born, glowing in their red cocoons at the edge of the visible past, too big and too old for any theory we have, still being puzzled over right now by people who do not yet know the answer. And there are the smallest ones, the hypothetical ones, the primordial points that may have been born in the first second of everything, that could be as small as an atom, that could be the most numerous objects in the entire cosmos, that could be drifting through the room, through the wall, through the ground beneath you, through you even now, and you would never know, and it would not harm you, and it would simply pass on into the dark, carrying its tiny impossible secret with it. The whole family, from the largest to the smallest, from the first second to the last, every type, all of it real, or possibly real, all of it out there, all of it part of the same single idea that a dying man found in a trench more than 100 years ago. The idea that mass crush small enough will close a door in space that nothing can ever open again. And here is the thought to carry down with you into sleep, the one to let your mind rest on as everything else goes quiet. All of these objects, every monster and every workhorse and every invisible point, are governed by the same simple rule, and they form a single connected family, stretching across every scale the universe contains. The same physics that makes the tiny ones makes the giant ones. The same boundary, the same silent door, the same slow eventual fading into a final flash. The universe is not a collection of unrelated wonders. It is one thing, deeply unified, the very large and the very small woven from the same law, the death of a star and the heart of a galaxy, and the dark matter that may hold everything together. All of it the same idea expressed at different sizes, and we, somehow small and brief, and made of the ash of dead stars, have managed to figure a great deal of it out, to weigh the unseen, to hear the colliding giants, to photograph the abyss, and to know, with quiet honesty, exactly how much we still do not understand. You do not need to hold any of it. That is the gift of a night like this. You do not need to remember the names or the numbers or the masses. You only needed to take the walk slowly, through the low and quiet halls, past every member of the family, out to the edge of the visible and back down to the smallest hidden thing, and now the walk is done, and you can set it all down. The black holes will go on without your attention. The giant at the centre of the galaxy will keep its slow vigil whether you think of it or not. The stellar remnants will drift through the dark. The hypothetical